So you sent us this thesis about Calabi manifolds, huh?
Yeah,
That's some pretty high-level math we're talking about here.
it is. It is. It's a fascinating area of mathematics.
But that's what these deep dives are for, right? To
Yeah.
take these really complex ideas and try to unpack them.
Absolutely. And you'd be surprised, it's actually really relevant to some of the biggest questions we have in physics, especially when we start talking about string theory.
Okay, so let's try to break this down.
Yeah.
For those of us who, might not have encountered these before, what exactly is a Calabi manifold?
Okay, so imagine a shape,
Okay,
like a sphere.
like a basketball.
Exactly. A basketball, a planet, you get the idea.
Yeah.
And one of the ways mathematicians describe these shapes is with a property called curvature. And you can picture it literally like if you think about a sphere, it curves inward.
Right, makes
Now,
sense.
Calabi manifold is a bit of a different beast. It exists in more dimensions than we can really visualize. 6, to be precise.
6 dimensions. Okay, now we're getting complicated.
Right.
Yeah.
But the important thing is that they're flat in a very specific mathematical way, of course.
So it's like a sphere, but it's been, what, like flattened out or something? I don't even know if that's the right image.
Kind of. It's like if you took a sphere and smoothed it out in these extra dimensions that we can't even see.
Okay. So we've got these like multi-dimensional flat shapes. Why should I, as someone who, didn't major in math, why should I care about
Well,
this?
because physicists believe that Calabi manifolds might actually be kind of woven into the very fabric of our universe.
Okay, now that got my attention.
Yeah. And it all comes down to this theory called string theory, which tries to explain how gravity works at the absolute tiniest level. I mean, much, much smaller than an atom.
And string theory, that's where all those extra dimensions come in, right?
Exactly. And it suggests that these extra dimensions, instead of just being kind of, out there, might actually be curled up in these incredibly complex shapes. And you guessed it. We're talking Calabi manifolds.
So this thesis that you sent us, it's like diving into the nitty-gritty of these Calabi manifolds and what they might tell us about the universe at that level.
Exactly. So it starts off with something called the Calabi theorem.
Okay.
Now, I'm not going to lie. The actual proof of this theorem is pretty dense. We're talking like really advanced calculus here, stuff I wouldn't want to do on a whiteboard.
I appreciate that.
But the key takeaway from the theorem is that it proves these manifolds, these shapes, they actually exist. Mathematically speaking, that is. They're not just some theoretical fantasy.
So we're not chasing mathematical unicorns here. That's always a good thing.
Definitely not. And it gets even more interesting, I promise. This thesis actually constructs a specific example of something called a Calabi metric.
Okay, hold up. Calabi metric. I'm getting flashbacks to high school geometry here, and they're not all good.
Uh-huh. Yeah, that term can sound a little intimidating.
Just a bit.
Okay, so think of it this way. Imagine you have this really complex, multi-dimensional sculpture.
Okay, I'm trying.
A metric, in this context, is basically a way to measure all the features of that sculpture, the lengths, the angles, the curvatures, so that you could recreate it perfectly even if you couldn't see it all at once.
So the thesis found a way to, measure a specific Calabi manifold. Why is that such a big deal?
It's a big deal because it takes these abstract, multi-dimensional shapes, these things we can barely even picture, and it brings them into the realm of the concrete.
So it's like saying, look, we can not only imagine these things, but we can actually describe them with some kind of precision.
Yes, exactly. And the specific mathematical object they did this on, it's called the canonical bundle of complex projective space.
Catchy.
I know, right?
Yeah.
But it's like finding a rare flower in the rainforest. It tells us there's a lot more out there to discover.
This is already blowing my mind, and we're just getting started.
All right, so let me see if I've got this straight. We've got these mathematically proven 6-dimensional flat shapes, our Calabi manifolds, as they're called, and they might just be the key to understanding the universe at its smallest level. How does that even work?
Well, that's where string theory comes in. You see, string theory asks this really wild question. What if, instead of the universe being made up of tiny particles, like little billiard balls, what if it was actually made of tiny vibrating strings?
Okay, so like guitar strings, but on a cosmic scale or something.
Exactly. And just like a guitar string can vibrate in different ways to create different notes, these strings could vibrate in different ways to produce all the different particles we observe. Electrons, quarks, photons, all of them. Okay, I think I'm following so far. But where do our friends, the Calabi manifolds, actually fit into all of this? Are you saying that the shape of these 6-dimensional spaces somehow affects how the strings vibrate?
That's the incredible part. It's like, think about it this way. The shape of a musical instrument determines the sounds it can make, right?
Right, a flute sounds very different from, like, a trumpet.
Exactly.
Yeah.
And in a similar way, the shape of a Calabi-Yau manifold, according to string theory at least, it would actually constrain the ways those tiny strings can vibrate.
And those vibrations are what determine the properties of the particles, the forces, everything. So are you saying that different Calabi-Yau shapes would mean different particles and forces, essentially different universes?
Now you're getting it. It's like the universe is this grand cosmic symphony, and the Calabi-Yau manifold is the instrument. Change the shape of that instrument, you change the music of reality itself.
Okay, my mind is officially blown. But this thesis you keep coming back to, it's not just about these big, universe level implications, is it? You said it gets into some really, really deep mathematical territory too, right?
Oh, it absolutely does. And that's actually where I think it gets even more fascinating. This thesis, it dives into some crazy cutting-edge concepts in geometry and topology, really pushing the boundaries of what we even know about these Calabi-Yau manifolds. Like, for example, it looks at this thing called supersymmetry.
Oh, yeah, I've heard of that. Doesn't supersymmetry suggest that every particle has this kind of super partner particle, like a
Yeah.
secret twin or something?
You got it. Which is kind of mind-blowing when you think about it, except for one small thing.
What's that?
We've never actually observed any of these superpartner particles in the real world. And scientists have been looking, really hard.
Yeah, that does kind of put a damper on things, doesn't it?
Right. And it's a bit of a problem, not just for supersymmetry, but maybe for string theory too, because a lot of the math behind string theory depends on supersymmetry being true.
Right, so if supersymmetry isn't actually happening.
Exactly. And this is where this thesis takes a really fascinating turn. The author is exploring ways to break supersymmetry, for lack of a better term, while keeping the core ideas of string theory intact.
Break supersymmetry. What does that even mean?
So, one possibility the author looks at is that the shape of the Calabi-Yau manifolds themselves, those six-dimensional shapes we've been talking about, might actually be the culprit. Remember we were saying that the shape of the manifold determines how the strings can vibrate? Well, they're investigating whether certain Calabi-Yau shapes could actually prevent those superpartner particles from forming in the first place.
So it's not just about like having those extra dimensions, it's about how they're shaped and folded into these Calabi-Yau things. That's kind of wild when you think about it.
Yeah, it's like saying the geometry of the universe, at its most fundamental level, is what determines the types of particles that can even exist. And this thesis is exploring the math behind that.
That's a lot to wrap your head around.
It is. But that's not even the only rabbit hole this author jumps down. They also get into something called Lie algebroids, which, I'll admit, even I had to brush up on.
Okay, that one does sound a little intimidating, even for this deep dive. Can you at least try to break it down for us? What are we even talking about here?
Okay, so think about it this way. So far, we've been talking about Calabi-Yau manifolds as if they're these fixed, unchanging shapes, right?
Yeah.
Like that sculpture analogy we were using earlier.
Like a cosmic sculpture. I like that.
But Lie algebroids, they offer this way to think about these shapes more dynamically, almost as if they're evolving over time, or maybe even in response to different conditions.
Wait, hold on. So you're saying that these Calabi-Yau manifolds, these shapes that are supposedly woven into the fabric of reality, they might not be static after all. They could actually change.
That's what the author is exploring. And it's some really, really out there stuff. It's like taking everything we thought we knew about these Calabi-Yau manifolds and adding this whole other layer of complexity and potentially a whole other level of insight into how the universe works.
My brain is officially in awe of this thesis. What an amazing journey it's taking us on. Okay, I need a minute to, catch my breath after that. We've gone from six-dimensional shapes to vibrating strings to the universe being a symphony.
It's quite a ride, isn't it?
It is. But as we, resurface from this deep dive, what's the, I don't know, the overarching theme here, the thing we should be really thinking about?
Well, what I find so fascinating about this thesis is that it's not just about finding answers. It's about asking new questions. Even bigger questions like, remember those Lie algebroids we talk about? Those dynamic Calabi-Yau
I
structures?
think those are pretty wild.
Yeah. So the very last section of this thesis, you know what it's titled, Calabi-Yau Lie algebroids in string theory, with a question mark.
With a question mark, so they're not even sure.
Exactly.
That actually makes me feel a little bit better. Even the experts are still trying to figure this stuff out.
Oh, absolutely. This is bleeding edge theoretical physics we're talking about here. It's okay to lean into the mystery a little bit, be comfortable not having all the answers.
I like that. But I still have to ask, how could these Lie algebroids, these potentially shifting shapes, how could those change how we think about string theory, like in a practical sense?
Okay, so let's connect this back to the bigger picture for a second. One of the, I don't know, the biggest challenges that string theory faces is that it actually predicts this mind-boggling number of possible universes, each with its own set of physical laws.
Yeah, it's like a cosmic dartboard.
Kind of. It's like this cosmic library with an infinite number of books, and each book describes a different universe.
Okay, I've heard of that. That's the string landscape problem or something, isn't it? Makes it kind of hard to prove a theory when there are infinite versions of it, right?
Exactly. And that's where these Lie algebroids, they might actually offer us a path forward. Because if Calabi manifolds aren't static, if they can actually, like, evolve maybe in response to the energy of the strings themselves, or who knows,
Yeah.
then, well, that could potentially narrow down the possibilities. Instead of an infinite unchanging library, imagine this dynamic system where certain Calabi shapes and therefore certain universes are more likely to form than others.
So it's not just like random chance which universe we happen to live in. There's some deeper structure there guiding the formation of these Calabi manifolds. And maybe, just maybe, these Lie algebroids are part of that structure.
That's one of the really exciting possibilities this thesis suggests, yeah.
This has been, seriously, an incredible journey. We've covered so much ground.
We have.
But I have to ask, for someone like me, and I imagine a lot of our listeners out there too, who, maybe didn't spend their college years doing higher math, why does any of this actually matter?
Beyond the, I don't know, the just mind-blowing science of it all,
Mhm.
what I find so compelling about these ideas is that they remind us of the just incredible beauty and mystery of the universe at its most fundamental levels.
Yeah.
Even if we don't fully grasp all the mathematical intricacies, we can still like step back and appreciate the elegance, the sheer audacity of imagining that the fabric of reality might be woven from these, intricate higher dimensional shapes.
And that the symphony of the universe, as we've been calling it, might be playing out on an instrument that's constantly changing, evolving, responding to the music itself.
Exactly. I love that. It adds this whole other level of wonder and complexity to our understanding of the cosmos.
Well said. For our listeners who've been on this incredible deep dive with us today, I highly, highly recommend going online, looking up some visualizations of Calabi manifolds,
Oh, yeah.
because they're surprisingly beautiful, even if we can't quite wrap our heads around the whole six-dimensional thing.
You never know.
Yeah.
That visual exploration, it might spark your own curiosity, lead you down your own path of discovery.
I love that. And on that note, we'll leave you with one final provocative thought. If these shapes, these Calabi manifolds, are constantly in flux, always evolving, what does that say about the nature of reality itself? Is anything truly fixed, or is everything in a state of constant change and becoming? Something to ponder until our next deep dive.